All right. So welcome to STAT 313, lecture 18. So last time we considered the theory of the analysis of variance or theory of ANOVA. So today we'll be doing some examples based on that to start with, okay? So let's get started. So let me remind you very briefly what we have done in the last class. So in summary, we considered these two quantities. So first of all, we computed this Q4 over B minus 1, which we call the mean square between groups, or MSB, and then Q3 over N minus B, which we call mean square within groups. Okay, so this is corresponding to different buckets, and this is inside the same bucket in a way. And what are those quantities? So I think we have written here. So for example, what is this Q4 and what is this Q3? So I think it's written right here. We have defined it before that. So here is the Q3. So Q3 is this quantity, and Q4 is this quantity. So Q3 is basically you're taking so the difference between xi bar, meaning that for a particular bucket, the mean and the and the elements for that corresponding one, and then you're sort of taking all the sums. So that is the Q3. That is what we call sum of squares due to the error. And then we also computed this Q4. So this is Yj bar is the mean of a particular bucket. And then we computed the other one. So this X double bar is a grand mean. We call it grand mean. So the average of all those quantities. Okay, so that is what we called X bar. And then it's multiplied by Nj. So remember that Nj was the number of elements of the jth bucket. Okay, what I mean by bucket was right here, we drew this picture, remember? So we have various buckets where the first one has total number of elements N1, the second one N2. So you see N1 number of elements here, N2 number of elements here, NB number of elements here. So that's what I mean. And so for example, here, the mean is given by X1 bar. Okay, so the observed mean is x1 bar, and where the population mean is mu1, where the observed mean is mu x2 bar, and the population mean is mu2, and so on. And what was the hypothesis that we are going to test? So that is the same as before. So the hypothesis is this one. So if all the means are same versus two of the means are different. Okay. All right. So we know all the theory, but now there is a very nice way of dealing with this one. And the theory is basically if this F value, which is MSB over MSW that we have defined in the last class, if this is big, then we reject the null hypothesis. Okay. Now, there is a very nice way of computing this. Okay, and that is the so-called ANOVA table. Okay. So here is the first thing we'll be doing. Say, and this is really helpful for computations. ANOVA table. One way ANOVA for one-way classification data. Okay. Just like we are discussing so far. One way because so our response is just we are thinking about just one response. Okay. So here are the two things. So we can have two different sources of variation, right? So we can have one source of variation is due to the internal things of the groups or classes, and the other one is for the is between the groups or classes. Okay, so let's write sources of variation, and we'll be writing here, say, between classes or groups, whichever you prefer, and within groups. Classes or groups. Okay, those are the two sources of errors, right? Next, we have a column called degrees of freedom, and we have seen that there are two different degrees of freedom. So the first one, so I'm talking about this one. So note that this is between groups and this is within groups. So when it's between groups, its degrees of freedom is b minus 1. And when it's within groups, it's n minus b. That's the degrees of freedom, right? Now we write sum of squares. Okay, so SS was the sum of squares. So I think we defined this SS here, right here. So SS is the sum of squares, which is Q. So SS between the classes. So this is going to be, so actually we have proved last time a very nice result, which I forgot to mention. So it's basically what we said here. When we say Q equals to Q3 plus Q4, this is really sum of squares equals to the Q3 is our SSE plus SSB. Okay, so that is the relation. Sum of squares is sum of squares SSE plus SSB. Okay. All right, so let's write. So the first one is SSB. And what is SSB? Well, so this is summation. I'll just write it for the completeness. So it's j from 1 to b n sub j xj bar minus x bar squared. And then here it's SSE, which is really j from 1 to b, I from 1 to n sub j xij minus xj bar squared. So that's the sum of squared. Okay, and I'll just put a mark here. Okay, and then based on this sum of errors, we can say the mean square error. So we can sometimes write this as MS. So this is mean square error between the groups. So this is the quantity MSB, which is SSB. I'm talking about this one. MSB is SSB. This is SSB over B minus 1, right? So this is really SSB. SSB over B minus 1. And then MSE equals SSE over N minus B. So this is really SSE. Okay. You compute this, and then you have from here the F value to compute the observed and here is the theoretical. Okay. What is the observed value? So this is really MSB, which is this one, divided by MSE, right? And what is the theoretical value we are talking about? Let me just write this way. So it's a f of say critical level significance level is alpha. So the numerator has b minus 1 degrees of freedom, and denominator has n minus b degrees of freedom. So that is the observed value, and that's it. So here, if this value is bigger than this theoretical value, then we reject the null hypothesis. If this value is less than this one, we accept the null hypothesis. Okay. By the way, I can also write here a total for the first two. So degrees of freedom is added. So it's n minus 1. This is also added. So because we know that when I have the SSB plus SSE, so this is really the SS, right? So it's really J from 1 to B, I from 1 to n sub j, xij minus x bar squared. We have seen that this sort of it gets distributed, or it's it's a very famous result that SS can be split in two parts. One is SSB, and the other one is SSE. Okay. Now, so that is pretty much it. I'll not write the other ones because the other ones were not very important. So I'll just put here dash. Okay. So this is the famous one-way ANOVA table. And from this, we'll be concluding things. Okay. And I'll be now showing you how to make this work. Now, before doing that, for the practical computation, there is some, I mean, of course, we can compute everything and do it, but it's customary to make some practical tweak to this. Okay. What I mean by that is the following. So when we are really dealing with a data, so then what we do is, suppose we are given with, say, classes. So here is for our given data set. Suppose we have different classes or groups. And I write, say, A1, A2, all the way up to AB. So this is the name of a group. We'll see some example very soon. This is for computational purpose. And then the values here are X11, X so we have X11, the first one, and then X21, X31, all the way up to X1N1. Here is X12, X22, X32, it's XN11, right? So here is XN2, 2, and similarly here, it's X1B, X2B, X3B, all the way up to XNB, B. Okay. Now here, we'll call the totals. So the first one, we'll call this as total of this one to be T1, T2, this is T sub B. Okay, so and we'll be denoting this as T sub, say, I. Okay. So I from 1. If you don't like this I, so let's use K because we have already used I and J. So this so this I is, I mean, if you recall the very first thing that we wrote in the last class. So remember that we have I from 1 to nj and j from 1 to b. So it's basically j. So let's call this t sub j. So the grand total t is really summation j from, so j is 1 to all the way up to b, t sub j. Okay, that's just this total. Okay, now total square tj. So if I total of squares, if I want to compute the total of squares, that would be given by summation. So here it's a square. The second number is always 1, right? So the first number varies. So the first number is changing on the I1 squared, and I runs from 1 to n1. Total of squares for this one is 1. Okay, let me just write this way. So this is I from 1 to n1 x of I1 squared. This is x of I2 squared, I from 1 to n2. Okay, so similarly here, it's summation I from 1 to nb x of I b squared. That's the sum of the squares of all this. And number of observations. So number of observations. Here, in the first case, there are n1, here it's n2, here it's nb, right? So therefore, I can write, say, so this number of observations, so if I write tj squared over n, so tj squared over nj would be, in this case, t1 squared over n1. You'll see why I'm using all this. T1 squared over n1, t2 squared over n2, and this is t of b squared over nb, right? Now, the total, the sum of squares, which we wrote before. So the sum of squares are written right here. So it's summation I from 1 to, let me just write it. So it's j from 1 to b, I from 1 to n sub j, xij minus x bar squared. You can check that this can be really written as summation j from 1 to b, summation I from 1 to n sub j, xij squared, okay, minus t squared over n. Okay, it's a very simple proof based on whatever we have done. Like it's a very similar, like the way we derive the variance. So this is how we can do it. Okay. Incidentally, this quantity we can know from this table. So here the total, the grand total we wrote for the case of this column, and here total is given by summation j from 1 to b, I from 1 to n sub j, xij squared. So if I compute, if I have this table, I can easily compute this quantity from the table, and then t squared over n, it's done. Okay. I'll leave it up to you to show that SSB, which is really summation j from 1 to b n sub j, xj bar minus x bar squared, that can be written as summation tj squared over nj, j from 1 to b, minus t squared over n. How do we get this number? Well, so that this is the total of this one. So total summation j squared over nj, j from 1 to b, right? So you see this table is sort of giving you all the information. So SSB is done. SSE is really the total SS. So this is sometimes like what we wrote here is the total SS, total sum of squares. The sum of squares is broken into parts, right? So what we have, we know that the total SS is the SSB plus SSE. So SSE is total SS minus SSB. Once it's done, almost the mechanical computation for me. So MSB is SSB over B minus 1. MSE is SSE over N minus B. And F observed is MSB over MSE. Okay. Now we can use the ANOVA table. Okay. So this is the procedure. And now let's see how to do it. So this is this is what we did here is a computational way. Computational way for ANOVA. I mean, this is in practice, we compute this way. So you'll be given with the data. I'll pretty soon do an example, and then we'll be considering all this. And then based on that, we'll be computing the appropriate values. Okay. So now it can be only best shown by an example. So let's take this. So let's take an example. So here is an example. This goes like this. A simple random samples of electric bulbs produced from 3 machines show the following data on life in hours of 3 bulbs, of these bulbs. Okay. So here is the table. So machine 1, machines and life of bulb. So machine number 1, so this is 1500, 1540, 1520. Machine number 2, 1560, 1530, 1540, 1545. Machine number 3 having 1550, 1540, 1535, 1540, and 1545. So there are the 3 machines, and this is the data. So what is the question that we're trying to answer? So here's the question. The question on next page. So the question that we're trying to address is the following: that analyze the data to test whether the average life of the bulbs produced from 3 machines are equal or not. Okay. Also, it's given that the upper, so this is the F values are given. So upper 5% and 1% points of F distribution with degrees of freedom 2 and 9 are 4.26 and 8.02 respectively. So it may be given, it may not be given, doesn't matter. I mean, if it's not given, we can always find it from the from whatever we have. Okay. All right. So what is the null hypothesis we are testing? So let's write the solution. So here's the solution. So H0 is basically we are testing the null hypothesis that if the 3 machines are having the same average life. Okay, so let's see. If I denote say, let's write first. Let Xij denote the life in hours of the, remember, so let's I mean, it can be done both ways, but our notation is, so we have 3 machines here. So the machine number is always written. So if it's from the first pot, we write the number at the end. It's from the second pot, we write 2 everywhere, right? So our machine number should go at the end. So this J should be the machine number, right? And I should be the bulb in that machine. Okay, so so Xij denote the ith bulb in the jth machine. So in our case, ith bulb. So how many? So bulbs can be for the machine 1. How many bulbs are there? So for machine 1, there are 3 bulbs. Machine 2, 4 bulbs. Machine 3, 5 bulbs. Okay. So basically, we have this data. So for machine 1, so we have 3 bulbs. So it's X11, X21, X31, and then we have X12, X22, X32, X42. So this is for the machine 2. And for machine 3, we have X13, X23, X33, X43, X53. So this is for the machine 3. This is for machine 2. or I think you use Roman. So let's use Roman here. 1, 2, 3. So this is for machine 2, and this is for machine 1. All right. So you see that, so that the notation wise, it's clear. Now, what is the null hypothesis? So the null hypothesis is H0 is they are from the same, they are having the same average. In the population, they have the same average. So how do you write it? So I can write this as a mu1 equals mu2 equals to mu3 versus H1 is mu of j is not equal to mu of j prime for some j not equal to j prime, meaning there are two machines which are having different average lifetime. Okay? So that's the hypothesis we are trying to test with ANOVA. Okay. Let's do it. And we have a very powerful table now. So let's use this table to compute it. So let's see. I'll just draw this picture in the same way as before. So the last time we wrote machines. So it's 1, 2, 3, right? What are the values? So the values are, well, so here it's 1500, 1540, 1520. Here it's 1560, 1530, 1530, 1540, and 1545. Okay. And for third machine, we have 1550, 1540, 1535, 1540, 1545. That's it. Okay. What do you compute? First, just compute the total. Okay. Now you see these numbers are awfully big. So there is another way of computing it. So it's by using I mean, you can try to shift these numbers by something that will not change the result. So let me just write it here. So the result, the final result, which is based on the variance. Remember, variance is not affected by the, if I add or subtract a constant from the data, it does not affect the variance. Okay. At the same time, if I have if I have a scaling factor, that affects it, but so what I mean is variance of ax plus b. So it does not see b. This a is seen as a squared. So shifting does not affect the variance, but scaling does. So scaling is reflected as a square. Okay. So what we can do is not affected by shifting. Okay. So this scaling is sometimes called the unit. Okay. So that means if I suppose I'm using the unit for say 5 pounds is my unit. Okay. So then when in my final results, this is reflected as the square of that. All right, so here is a computation, another way of computing this computation. We shift the origin to 1540 from this data and take 5 as unit. the new values become the following. So let's write this. The first one, second one, third one. So what we did is basically, the old value. So this is what you're doing. New equals to old minus, we are subtracting 1540 and divide by this 5. That's what we're doing. So these values are becoming, you can check, -8, 0, -4, 4, -2, 0, 1, 2, 0, -1, 0, 1. Much simpler. So what is the total here? So total, which I wrote as T sub j. So this is T1 is -12, T2 is 3, T3 is 2. So the grand total, T is the sum of these three, is -7. To 3 is -7. So that we are adding up. Okay, that's the first thing that we did. So what I mean is I'm now looking at this picture. That's the first thing that we did. And then this total of squares. So let's do that. So total of squares. Or sum of squares. Which is given by summation x ij squared. And in this case, so my data is now shifted, like it is something like this one. So I'm just using I from 1 to nj. So in my case, it's whatever. Let me just write it I or summation on I, because it differs for 3 different cases. They're different. All right. So for the first case, note this. So for the first case, this is going to be x of I. So in this case, I'm just taking the sum of squares of these 3 numbers, right? So it's essentially -8 squared plus 0 squared plus -4 squared. So it's 80. In the second case, it's 4 squared plus -2 squared. So 4 squared minus 2 squared plus 0 squared plus 1 squared. So which is 21. And in the third case, it's 2 squared plus 0 squared plus -1 squared plus 0 squared plus 1 squared, which is 6. So the summation of the total sum of squares, so xij squared in our old notation, so this is going to be I from 1 to nj. So this is going to be j I from 1 to nj and j from 1 to b. So this is the sum of these 3, which is really, so it's 80 plus 21 plus 6, which is 107. Okay, that's the second one. And now, so we are done with this one, we're done with this one. So number of observations. So let's see how many number of observations here. So number of observations. Which is in the first case, we have 3, and here it's 4, here it's 5. So total n equals to 12, right? Now, so we considered this ti squared. So after this one, we computed this tj squared over nj. So that means it's number of observations were nj. So we divide the tj, which we obtained in the first step, by this one. So let's compute this. So we computed tj squared over nj, where these are my tj's. So basically it's minus 12 squared over 3, which is um, 48, and you get the idea. So the second number is going to be 3 squared over 4. So it's 2.25. And here it's going to be 2 squared over 5, which is 0.8. So the summation, so total is going to be, if I add all this thing, so it's going to be 51.05 approximately. Okay, or actually exact. Okay, so up to this understood. Now total sum of squares, total SS. I'm going to the next part of the table, total SS. So how do you compute this? So I don't need this table here, sorry. So the total SS, so total SS, I'll be now using all these values. So this is basically, note that, so this is this one. So summation I from 1 to nj, j from 1 to 3 in my case. Okay. By the way, so I should also write this. This is my, I mean, since it's important, so it's n1, n2, and n3. Okay. Okay. So this is xij squared minus t squared over n. I'm just writing this formula. How do I get t squared over n? So it should be it should be obtained before. So what is this t squared over n? So grand total is t, right? And n is the total number of observations. So this is here, the total is n. So basically, if I can divide the last for this, the first one and the last one, so t squared was minus 7 squared. So this quantity, so t squared over n is minus 7 squared over 12, right? Now we have to be a little careful here because we had done a shifting, right? So we have done the shifting of the values. Now, whenever we shift this, as I mentioned that so these the old values and so my new values are something like this one. Now, if I want to go back to the old one, so if I have to go back to the old one, so old one is really 5 times new plus 1540. So old variables are 5 times new plus 1540. Now this 1540 does not affect any computation for the variance, but this 5 does. How does it work? So this 5 is like A. So whenever I compute something to do with the variance, so then I have to multiply with 5 squared due to this formula. So here, so total SS for the original variable, not those new variable. So now I just multiply this by 5 squared. Okay, so this is going back to original variables. Okay. Rest is very simple. So how do we get this number? So this number should be here. So this number summation of this one, look at this, by the way, B is 3. So it's 107, right? So it's really 107 minus t squared over, so this is 49 over 12 times 25. 5 squared is 25. If you compute this, so this total SS is going to be 2572.92. Now, of course, you're welcome to use the original data and compute this. So that will be, you're getting the same answer, but here it's a little faster way of doing it. All right, so that is the total SS. What's next? So after this one, after we computed the total SS, what do we need? Here, SSB, the next step. How do you compute SSB? By this. So let's compute this. So SSB is really J from 1 to B. B in our case is 3. Tj squared over Nj minus t squared over n. And if we have done this computation the way I have done it here, all the numbers should be readily available. For example, this number here, which I didn't write, so this is really Tj squared over Nj, J from 1 to B, right? The last sum. So this is basically 51. Also, SSB is a number which is it's computed out of the squares. So that means if I have to go back to the original variables for SSB, I have to also make that correction. So it's basically times 5 squared. So this is again going back to original variables. Now, if you compute this, this is going to be, so let's see, this number is 51.05, and this is 49 over 12 times 25. If you compute this, so this is going to be, let's see. So this is 1174.92. And therefore, there's what's next. So then we'll compute SSE. SSE is the total SS minus SSB, which is, we have already computed both. So it's 12572.92 minus 1174.92. Sorry, it's not 92. It's 1174.17. So this is going to be 1398.75. This is already in original variable as both SSB and SS, total SS, are already converted. What I mean is you don't need that 5 square factor here. Okay, now let's compute the MSB. MSB is the SSB. So what I'm mentioning here is this one. So MSB is SSB divide. I'm trying to just find out the appropriate page here. B minus 1. In our case, B is 3. So it's 3 minus 1. So it's going to be 587.09. MSE is SSE over N minus B. So N in this case is 12 and B is 3. So it's SSE over 9, which is 155.42. And therefore, the F observed is MSB, MSE, which is 3.78. That's it. That's the computation. And now I can write this in a nice table and we are done. So now we can see. So the ANOVA table. So consequently, the ANOVA table looks like the following. Well, now we have all the information. Source of variation between machines, remember? So we wrote the source of variations between machines and within machine. So within machine means it's basically due to the error. Degrees of freedom. So then the first case, it's 2. Second case, it's 9. So here the total is 11. SS, total SS, which is given by, well, the first one is the SSB, which we found to be 1174.17. And then we have SSE, which we found to be 1398.75. So the total SS is 2572.92. Then MS. So the first one we found to be MSB. We found 587.09. MSE, we found 155.42. Okay, we don't really need the total. Now the F value. F value is observed and theoretical. I don't really need this middle line. So observed value, you find it 3.78. Okay. Now F value theoretical is already given. If you look at the problem, so the problem also provides you with the F value. It's given that degrees 2.2 and 9, 5% and 1% significance level, it's 4.26 and 8.02. Okay. So what is given is F of, say, if it's 5% significance level and 2.9, so that is given to be 4.26, and 1% degrees of freedom 2.9, its value is 8.02. And that is pretty much the table. Okay, that's ANOVA table. What do you conclude? Since, so this is F observed. Since F observed is less than F of 0.0529, so this is 3.78, this is 4.26. And F observed is also 0.0529. This is also true, of course. So that means so we accept H0 with 5% level of significance. And of course, if we can make it something with a 5% level of significance, so here it's obviously that we can also make it 1% level of significance. So in this case, 5% level of significance and 1% level of significance. Both are true here. In fact, since it's 5% level of significance, and therefore it's automatic, and therefore, and this implies 1% level of significance. Okay, so this is true with 5% level of significance. Therefore, it's true in 1% with 1% level of significance. So we accept H0 and conclude that the average life of the bulbs produced by the three machines seem to be equal. Okay, so that is the analysis of variance. So we have used, or we have implemented the analysis of variance for computing this. Okay. Next problem. So second problem. Example. It goes like this: a random sample, and now we can do it fast. A random sample of 5 motor car tires is taken from each of, so a random sample of 5 tires, so let's write this 5 car tires is taken from each of 3 brands manufactured by 3 companies. The lifetime of these tires as measured by mileage run is shown below. On the basis of the data, test whether the average lifetime of the 3 brands of tires are equal or not. And here is the data. So lifetime of tires and brand. So brands are A, B, and C, and lifetimes are in the unit is 1,000 miles. The first one is 35,000, 34, 34, 33, 34. Here it's 32, 32, 31, 28, 29. Here it's 34, 33, 32, 32, 33. Okay. So that's I mean, we have this setup. So let's do the calculation. Solution. Let's shift all the observation by 30. So I want to subtract 30 from everything. That will not affect the result, right? Shifting does not affect the result. So I can shift it. Okay, so let's do that. So then my table will look like A, B, C. So here it's 5, 4, 4, 3, 4. I have a smaller number to work with. So 2, 2, 1. Again, you don't have to subtract 30. You can just subtract any number you want. All the calculations will be same. 3, 2, 2, 3. Okay. So here, the total which is we wrote it as TJ. So it's T1 is 20, T2 is 2, T3 is 14. So T, the grand total, is 36. Okay, I'll write it in short now. Total of squares where we square and add. So this one will give you 82. I can check. Here, if I square and add all this, 2 square plus 2 square plus 1 square plus 2 square plus 1 square, 14, 42. So here, so we have I from 1 to n sub j, j from 1 to 3, once again, 3 groups, xij squared. So the sum of all these 3 is 138. Sample size, number of observations, which is n sub j. Well, we are given with n1 equals to 5, n2 equals to 5, n3 equals to 5. So n, the total number of observations, is 15. All right, so therefore, the next one, what we have is after total number of observations. So it's TJ squared. So these are TJ squared. And this is not really TJ squared. So what I do is, this is not TJ squared. So this is, I'll compute TJ squared over NJ. So the first one is 20 squared over 5. Second one is 2 squared over 5. Third one is 14 squared over 5. Okay. So here's the sum. So total is whatever it is, 20 squared plus 2 squared plus 14 squared over 5. Okay. Now, after this one, so that's pretty much it. So, and you can even make this table. So this. Now, let's compute the total sum of squares. And this is already in original variable as no scaling is used. We only used shifting. That does not affect results. Okay. So in other words, remember in the last problem, we are multiplying by that 25 because like 5 squared, because we had scaling there. But here it's only shifting, so it does not really matter. So now total is given by, it's really I from 1 to n sub j, j from 1 to 3, xij squared, minus t squared over n. Okay. So what is t squared over n? I forgot to compute this, which is very important. So let's do it here. So t squared over n is 36 squared over 15. Right? So which is 86.4. Now, how do you compute this? So everything should be there. It's 138. The first number is 138 minus 86.4, which is so this number is 138. It's 51.6. Okay. So that is the first one. Okay. The second number. So this is after we compute this. So now let's compute the SSB. So this is total SS. Now SSB is given by what? So it's given by j from 1 to 3 tj squared over nj minus t squared over n. Now, by the way, this number is also computed right here. So this is really total, means it's summation j from 1 to 3 tj squared. Okay. So this is given, so I can easily compute it. I'll not show the computation. It's very easy. It's 120 minus, so this is really 120. So it's 120 minus 86.4, which is 33.6. Okay. So SSB done. And now SSE. So SSE would be total SS minus SSB, which is 51.6 minus 33.6, which is 18.0. Okay, and that's pretty much it. I can, of course, compute MSB. So MSB is SSB so SSB over B minus 1. So in this case, so we have 3 groups. So it's 3 minus 1. So if you compute this, it's 16.8. And MSE is SSE over N minus B. So N is 15 minus 3. So it's SSE over 12. So which is 18 over 12, which is 1.5. Okay. So F observed is MSB over MSE, which is 16.8 over 1.5, so 11.2. Okay, now let's have the ANOVA table. So ANOVA table, it's basically just a nice way of putting all these results. So source of variation. Source of variation between groups, or in this case, what is that? Between brands and for the within brands. Okay, so now, so degrees of freedom. So this is 2 and this is 12. So now we have SS that we computed to be, so we have total, so SS, so the first one is SSB, which we computed to be 33.6, SSE, which we computed to be right here, 18.0. So the total SS is 51.6. Okay, and then we have the MS, which is the first one is MSB, which is SSB over the degrees of freedom, which is 16.8. This is 1.5 MSE. We don't write the last number here. And that's it. So now we have the F value observed and theoretical. Okay. Observed value we found just now, it's 11.2. F observed. And now F theoretical with the, so our degrees of freedom and 12. So from the table, we can get that zero, or from other sources. You can have free online library to get this number. So with 5% significance level and 2 and 12 degrees of freedom, this number is 3.89. And if I have, say, 1% significance level and degrees of freedom 2 and 12, this is going to be 6.93. Okay. Now, since the observed value, which is 11.2, exceeds 1% tabulated value, that is a theoretical, and in effect, so this exceeds 5% theoretical value. Okay. Conclusion is we reject H0. And conclude that the average lifetimes of the 3 brands of tires are not equal. That's the conclusion. So that's the answer for this case. So there are 2 different examples. Remember, in the previous example, we have seen the case when we did not reject the null hypothesis, but this is an example when we see that this is the case when we reject the null hypothesis. Okay? Let's do one more. So this example, so the last example, it's very simple. So it goes like this. Each of the following sets of observations is a random sample from a normal distribution or normal population. So here are the sets, here's the observations. So it's given a set as 1. The observations is 249, 242, 247, 250, 252, 2, is 251, 256, 255, 258. 3 is 266, 261, 265, and 264. And the fourth group is 262, 260, 263, 262, 261, 264. This is a bigger group, 262. So these are the four groups. Okay. Test whether the population means are equal. And assume that the population standard deviations, because I said normal population, standard deviations are the same, So we are not really testing that. Okay. Okay, so here is the solution. So we start by writing the null hypothesis. So H0 here is suppose population means are equal. H1 for all four groups. And H1 is at least two groups will have different population mean. Okay. So the first one is saying that all the four groups are having the same average as our same mean. And the second one is saying no, at least two will have the different mean. So that's the null hypothesis and alternative hypothesis. So now let's consider the data. So now since the data, I mean, if you look at the data, it looks like it's around 250. Okay. So what we'll be doing is we'll be subtracting 250 from everything. Okay. The observations are shifted by 250. Okay, for the easier computation, for nothing else. And again, it's only the shift, so it will not affect anything, because remember, the scaling affects things, but shift does not affect anything. So then I have these four groups, 1, 2, 3, and 4. So if I have reduce those numbers, so it's -1, -8, -3, 0, 2. Here it's 1, 6, 5, 8. Here it's 16, 11, 15, 14. And here 12, 10, 13, 12, 11, 14, 12. I'll just follow the procedure from the last one. So the total, which we call T sub j, is given by here. It's T1 is -10, T2 is 20, T3 is 56, T4 is 84. Okay. So that means the total T is the sum of all this, which is 150. First one. Okay. Then if you look at the last problem, the next one which you compute is the total of squares, where I'm squaring and adding this. Okay, so here it'll be 78. Here it will be 126. Here it's 798. Here it's 1018. And hence, here this quantity j from 1 to, so we have 4 groups. And each group we are having different candidates. So n sub j xij squared. So this number is, if I add all these 4 numbers, it's 2020. Okay. Now the number of observations. So it's N1 is 5, N2 is 4, N3 is 4, N4 is 7. So total N is 20. And finally, I'll be computing Tj squared over Nj. So Nj's are here, Tj's here. So it's T1 squared over, so it's minus 10 squared over 5. Here is 20 squared over 4. Here it's 56 squared over 4. And here is 84 squared over 7. So if you compute this number, so it's going to be, the way we wrote it is total, which is summation Tj squared over Nj. J runs from 1 to 4, which is 1912. If you add this 4, you'll get that. That's pretty much it. Okay. So now let me just close up this table. Okay. Now let's first compute the quantity that we'll always need, T squared over N. So T squared over N is 150 squared over 20, which is 1125. If I have this, so total SS, remember that this is same as the already in original variables, as only shift was used. Remember that we started the observation by shifting 250, so that's just a shift, so that does not change the total SS. Okay, so what is that? So it's going to be j from 1 to 4, I from 1 to n sub j, xij squared minus t squared over n. Now, all these numbers should have been already computed. It's 2020 minus this number we just computed. It's 1125. So it's 895. That's the first number. Next, SSB. So SSB is given by summation j from 1 to 4 tj squared over nj minus t squared over n. Now the first one is already computed right here. Okay. So it's 1912. So this number here is 1912. So 1912 minus 1125. 1125 is t squared over n. So if I compute this, so it's 787. So SSE would be total SS that we computed at the end of last page minus SSB, which is therefore 895 minus 787. Okay, so we computed 895 before, and then here we have 787. So this is going to be 108. And consequently, the MSB which is SSB over the degrees of freedom. So in this case, it's we have 4 minus 1. So if we are dividing SSB 87 by 3. So which is 262.3. And MSE is SSE over N minus B. And N in this case was, this is N20. So 20 minus B was 4. So this is really 108 over 16. So it's 6.75. And hence, F observed is MSB by MSE, which is 262.3 over 6.75, which is 38.9. So the ANOVA table, I can now list everything very nicely. So here is the source of variation. Between, so here we say that there are 3 different sets. So between sets and within sets. Okay. Then we write degrees of freedom. So for the first case, it's 3. For the second case, it's 16. Then we write the SS. So we write, and by the way, here for the first two, 16 plus 3, it's 19. So here it's a 787, it's 108, and the total was 895. Then we write the MSB and MSE. So MSB is going to be 262.3. MSE is going to be 6.75. We have already kind of calculated this. Okay. And that's pretty much it. We don't need this total. So now F, we write observed and theoretical. Observed, we found F observed. We found this value to be 38.9. And now with the help of like online table, we can find that F with 5% like significance level and 3 and 16 degrees of freedom, this value is 3.24. And 1% significance level with 3 and 16 degrees of freedom, that's going to be 5.29. So now let's see. This number is way, way more than this two. So since F observed is bigger than both the tabulated values, we reject H0. Conclude that the means of the sets are not equal. So that is the conclusion. Okay. So once again, this is a very standard trick, and we implemented the ANOVA to compute it. Okay. Now, this kind of problems are very useful, and we can use it pretty often to check a lot of different things. For example, if we have different brands or different classes, and we are trying to see if the averages are the same or not, or maybe two averages are different. So this is the technique we used. So last class, we did a theory of this. And today we have done based on the theory. So everything what we have done today is based on the theory. So based on the theory, we solve problems, and we have seen how this ANOVA can be used in practice. Okay. So that is it for today's class. So next time we'll continue with this topic. So thank you very much.